Okay, now the next title will be isomorphism. Iso means same. Isomorphism. See, for example, you have a linear transformation. You have set of vectors. You are going to perform some linear transformation, and you are going to get the same property on that side. So what we call this as isomorphism. Those vectors are called isomorphic. For example, when you take any matrix, in matrix we have some properties will exist. Determinant property is there. You have 3 by 3 or 3 by 2 matrix. Rank of a matrix, that also exists. Suppose I am going to perform one linear operation for a matrix, and I am going to get the same property on that side. That means these two matrices are come under isomorphism. These two matrices are called isomorphic. Any doubt? So isomorphism. So there will be a one-to-one correspondence between two sets. One-to-one correspondence. You are going to perform one linear operation, linear transformation of one matrix. You are going to get another matrix. These two matrices should have same properties. That's all. Okay. Two vector spaces U and V are isomorphic if there exists a linear transformation. T operates on U will give you V. T is a linear operation. Linear operator operates on U will give you V. In this we write U almost is equal to V. The properties of all U is nothing but V. Okay. And the linear transformation T is called as isomorphism between U and V. Okay. The term isomorphism originates from the Greek letter. It means same. We have same properties. So we are going to perform some operation. We are going to have a same property. The relation of isomorphism is an equivalent relation to the set of all vector space. We can multiply every vector in one space time and invertible. Invertible means this is nothing but isomorphism. Matrix to generate the second space. So this is first space. Everything comes under in linear vector space. You have a linear transformation of one space that will give you another space. Both will have same properties. All will come under linear vector space. Okay. And these are the operations that we know already. So for example, when you take U, you are going to have two components. For example, C1 U1 plus C2 U2, and you are going to have this rule for isomorphism. You are going to have this rule. Linear transformation of U which will give you V. U and V will have same property. They will have same properties. So T of V also will be C1 V1 plus C2 V2. This will belong to one space. This will belong to another space. But both will have same properties. So what we call this as isomorphism. U and V are called as isomorphic. So linear transformation is both one-to-one correspondence. So there will be one-to-one correspondence for U and V. They are all called isomorphic. When two vector spaces have an invertible linear transformation defined between them, we can translate about, for example, when you are going to take, as I said just now about vectors, you have certain properties. Rank, then whether matrix is 2 by 2 or 3 by 3, like that. Similarly, when you are going for vectors, the spanning property. For example, you have x, y, z. So this will span into 3 coordinates. Propagate into 3 coordinates. This is called a span in vectors. Linear independence, basis, dimension. So they are all properties of vectors. So those properties in the first space will be exactly equivalent to those properties in the second space. What we call this as isomorphism. Okay. Some properties. Spanning is one property. Linear independence is another property. Base is another property. Dimension is another property. Okay. The obtained results in the second vector space can then be translated back. We can also reverse also, it's possible. We can get back to the original one. We can get back. For example, you are going to perform with a linear operation of one vector, you will get another vector. Suppose I am going to have a reverse one from here to here. That also is possible. So it says that the obtained results in the second vector space can then be translated back via the inverse linear transformation. We call this as inverse linear transformation and interpreted in the first vector space. So we can go from first space to second space to first space. provided these two, u and v, first phase and second phase should be isomorphic. Is it okay? So we call this as isomorphism. So next title will be projection operators. Already we have seen the projection operator in Gram-Schmidt procedure. And two vectors or more than two vectors are not orthogonal, then we will have to make those vectors as orthogonal to each other. So this is what we discussed in the last class. And these vectors which are orthogonal, they are very related to ground state and the excited states. So that's the reason that orthogonal vectors are needed. We need to have orthogonal vectors. Okay, so two vectors are orthogonal, they must be perpendicular to each other. The answer for canonical delta function will be 0, we know already. So what we call this is using through projection operator only we have done. A21, A31, those are all projection operators. So those projection operators are very important in quantum mechanics. An operator P is said to be a projection operator if it is a Hermitian. Hermitian means just take a matrix. You have rows and columns. You are going to interchange rows and columns, take the complex conjugate, that will give you Hermitian. I repeat, in a matrix, just change the row into column and take the complex conjugate. These two operations are nothing but Hermitian. Either you can take transpose and you can take transpose means take the complex conjugate. Okay, and after that you can perform rows and columns. Either way it is possible. I repeat, see here, in a matrix, change rows into column and take the complex conjugate, or take the complex conjugate and change into rows into column. Both operations are the same. What we call this as Hermitian. It is denoted as dagger, D-A-G-G-E-R, dagger. So P dagger equals P. If this condition is satisfied, we call that operator is nothing but projection operator. 1. Second one is P squared must be equal to P. We square it, that will be the same answer. It is possible. Okay, P squared equals P. We are going to prove this one. We are going to prove. So P squared equals P. So P is a projection operator. You are going to square it. You are going to square it. The answer is the same thing. If these two conditions are satisfied, then we say that P is a projection operator. Okay. And this is in matrices. We call this as idempotency condition. Okay, in matrices this is termed as idempotency condition. Now for the projection operator, P is denoted as this symbol, ket with bra. So you have ket and this is your bra. Okay, so this must be an operator or a scalar. This must be a vector. The answer must be a vector. If it is bra with keter, answer will be a number, scalar. Here ket with bra. Now we are going to square it. Squaring the operator is very important rule. It should not be like a plus b whole squared. We should never go with the rule. A plus b whole squared equals a squared plus b squared plus 2ab. We know already. And this is not applicable for the operators. So very important one. So for example, we take a operator plus b operator whole squared, which is equal to a squared plus b squared plus ab plus ba. Is it okay? It is not 2ab if it is an operator. Otherwise it's very simple. For example, a plus b whole squared equals, we know the simple formula from algebraic rule, a squared plus b squared plus 2ab. Suppose if a is an operator, b is an operator, this rule will not be applicable. We will have to say like this, a squared plus b squared plus ab plus ba. ab is not equal to ba for the operators. Okay, just remember. So p squared means you will have to operate twice. See, I have operated twice. See, operation means p squared is there. P is given by this. P is given by this. So you have to square it means you have to operate again. So we have operated again. Any doubt? So instead of two lines, I can write a single line, as we said earlier. We discussed. Correct? What is this one? This alone? What is this one? Anybody? It's a scalar. Very good. It's a scalar. It's an inner product. Scalar product. So this must be, answer must be 1. So look over here, the answer is ket psi and bra psi, which is same as that of this. So p squared equals p. Very simple. So p squared equals p. Second one. Any doubt? So the unit vector I is a simple example of projection operator. Even I squared equals I. So unit vector is nothing but a projection operator. Very important one more question. Unit vector is nothing but a projection operator. Okay, any doubt? Unit operator is nothing but a projection operator. What are the properties? Properties, very important property is P1, P2. Suppose if you have two projection operators, P1, P2, which is equal to 0. This bracket is known as commutative bracket. Commutative bracket. The rule for commutator A, B equals AB minus BA. I repeat, see here, you have a commutator bracket. This bracket is known as commutative bracket. Commutative bracket A, B equals AB minus BA usually. Okay, if it is equal to 0 means this will commute with each other. This operator will commute with P2. P1 commutes with P2, which is equal to 0 means we call this as commuting operators, commuting observables. Okay, what we call this as commuting observables. Commuting means simultaneously you can measure. Non-commuting means you cannot measure. Probably you would have studied x, p equals Eigen cross. Quantum mechanics, most probably you would have studied in UG. Can you remember? X, p equals Eigen cross. The answer exists. In the commutative bracket, x, p equals Eigen cross. Eigen cross means it is not 0. It is Eigen cross. So answer exists. So both will not commute. So here commuting. You cannot measure x and p simultaneously at the same time. Here you can measure. So the product of two commuting projection operators P1, P2 is also a projection operator. Okay, for example, when you take P1, P2 dagger, just take P1, P2 dagger. Okay, and the rule says when you are going to take dagger, says this one will come first and this will go second. For all dagger operation, very important thing is this one will go into first one and this one will go into second one. So P2 dagger, P1 dagger. What is P2 dagger? It is P. P2 dagger is nothing but P2. P dagger is nothing but P. So your P2 dagger is nothing but P2. P1 dagger is nothing but P1. So we can write P2, P1 as P1, P2. Because this is commuting observable. A, B equals AB minus BA, which is equal to 0. So AB equals BA. So P1, P2 equals P2, P1. See P2. So P2, P1 equals P1, P2. Because it's a commuting observable. They are all commuting observables. Similarly, we can go for this side. Same P1, P2 whole square can be written also like this. So P1, P2 which is can be written as P1 square, P2 square, which is equal to P1, P2. Two projection operators are said to be orthogonal if the product is 0. So we know already this. The sum of two projection operators is generally not a projection operator. The sum of two projection operators generally will not be a projection operator. For sum of projection operators P1 plus P2 plus P3 to be the projection operator, it is necessary and sufficient that these projection operators mutually orthogonal. So they must be orthogonal. If they are orthogonal, then we can say they are projection operators. If they are not orthogonal, they are not projection operators. That's the conclusion. The last one is eigenvalues and eigenfunctions. So we discussed about eigenvalue earlier, but we are going to discuss clearly and elaborately here. So I repeat, this is your eigenvalue equation. A operator operates on the function, will give you eigenvalue with a function. If these two functions are same, we call this as eigenfunction. Okay, this is your eigenvalue. This equation is known as eigenvalue equation. So this is your operator. This operator can be, as I said, differentiation, integration. Many times you can differentiate. Squaring. Okay, those are all operators. Okay, adding, subtracting, multiplying. Yes, so everything is an operator. So an operator A operating on any function of the operator multiplied by a constant, so called as an eigenvalue of the operator. This equation is known as eigenvalue equation, and it is expressed as exactly like this. So where A is the eigenvalue of the operator. The function psi of x is called eigenfunction, provided these two functions should be the same. If they are not same, we call this as function or wave function. Okay, to the eigenvalue A. For example, this is an operator, operates on e power kx, which is equal to k e power x. What is k? Eigenvalue. What is e power kx? Eigenfunction. So because here e power kx is there, here also we have e power kx. So it's an eigenfunction. D by dx is an operator. This equation is known as eigenvalue equation. That's all. So e power x is an eigenfunction of the operator d by dx corresponding to the eigenvalue k. In general, we have a set of values a for which eigenfunction exists. For example, there exists more eigenfunctions. Then we can write, generally we can write exactly the eigenvalue equation as exactly like this, where we can have m equals 1, 2, 3. So a psi m stands for 1, 2, 3, 4 goes on, and you will have am, a1, a2, a3 goes on. So similarly we can write this as psi m stands for 1, 2, 3. So generally we can write. Suppose for one wave function we have one value. So this is the last slide. Okay, we have one wave function and one value, eigenvalue. We call this as non-degenerate. I repeat, we have one wave function. For one wave function we have one value. So this is called a non-degenerate. Suppose if there are many wave functions, we have a single value, we call this as degenerate. For one wave function, if you have one value, one eigenvalue, we call this as non-degenerate. We have many wave functions and we are going to have the same energy, same eigenvalue, we call this as degenerate. The same the same eigenvalues are obtained for different wave functions. Then the eigenvalues are said to be degenerate. If all the eigenvalues of the operator are discrete, it is said to have a discrete spectrum. So they will have only discrete energies. For each wave function, you will have one value. It's a discrete value. It is not continuous one. Okay. Some operators of the operator. For example, you have the operator square of the operator. Okay. We are going to perform like this. So O is an operator. Okay, it's squared. So O squared, which operates on one function, f of x a function, which is equal to, we can write the operator two times. See, O operator. Is it okay? So now I will return the same thing. O operator operates on this function will give me eigenvalue O f of x. Is it okay? I repeat. See here, I have written the same thing. First, this operator will operate on this. Operator operates on f of x will give me eigenvalue f of x. This O operator is here. I am not disturbing. This O operator is here. See, I am going to perform only this one alone. So operator O operates on f of x will give you eigenvalue O f of x. Is it okay? This is a value I can take anywhere. Operator should not be taken anywhere. This is a value. For example, when you take phi x, x phi, I can also write x phi, doesn't matter. But uniformity should be there. So now this O is a value. I can pull it out. So I have pulled out. Operator operates on f of x will give me this O, eigenvalue with f of x. So O multiplied by O will give me O square. We should not do directly. For operator, when you are going to square the operator, you will have to perform two times. A plus B whole square. If A is an operator, B is an operator, we should do A plus B multiplied by A plus B. You will have to perform two times. Only then you will get the correct answer, like A square plus B square plus AB plus BA. Okay, for operation and for the operators, we have to follow these rules. So far we started with linear operators, correct? Then after that linear operators, then we discussed projection operator, then after that eigenvalue equation, isomorphism, then eigenvalue, eigenfunctions, eigenvalue equation. Okay, we'll see in the next class. Bye students. Thank you.